So we begin with inequalities, and there are a few basic rules which inequalities adhere to. The first being a rather obvious one. Let's say we have two numbers A and B, with A strictly smaller than B. If you add any number to both of these numbers, let's say that number is C, be it positive or negative, then A plus C will be strictly less than B plus C. And very similarly to that, if you've now got four numbers with A less than B and C less than D, then the sum of the two smaller ones will be dominated or is less than the sum of the two bigger ones, B plus D. Thirdly, let's say the inequality A less than B is true, and if C is a positive number, then you can multiply by C on both sides of the inequality. And since C is positive, that's the important thing in number 3, the inequality will remain the same. So if you multiply by a positive factor, the original inequality is respected. On the other hand, if C is a negative number and you perform the same thing by multiplying by C on both sides of the inequality, then as you can see, if A was originally less than B, and because C is a negative number, then AC will be bigger than BC. Let's say we have two numbers A and B, both of which are positive and neither of them are 0. So A is less than B and A is strictly bigger than 0. Then taking reciprocals, or in other words, if you invert them, the inequality again flips. So if A is smaller than B and A is not, positive and non-zero, then 1 over A will be bigger than 1 over B. For example, let us solve the inequality. When we say solve an inequality, we perform the same operations as we do with equations. However, we respect the inequality rules, particularly when it comes to multiplying by negative numbers or taking reciprocals. And we want to find all numbers x which satisfies the given inequality, instead of particular solutions, as is the case with usual equations. Nevertheless, let's begin with this one here. 1 plus x is strictly less than 7x plus 5. We apply rule 1 in that we can subtract or add a number on both sides. Here we subtract 1 on both sides, and then we end up with x being less than 7x plus 4. Further, we can subtract by 7x on both sides to get minus 6x less than 4. And we want our solution to be of x alone, so we can multiply by negative 1 over 6, or in other words, divide by negative 6 on both sides. But notice that since we are dividing or multiplying by a negative factor on both sides, the inequality sign must flip. And so we get that the solution to this inequality is all numbers x strictly bigger than minus 2 over 3. And we can represent the solution graphically on the number line as follows. So this blue line traced over the number line represents all the numbers x which satisfies the given inequality. Since the inequality was strict, remember it was x greater than minus 2/3. We do not include the number minus 2 over 3 itself. So that is why there is an open circle at the number minus 2/3. And another way to represent this solution set is by using set builder notation. So we can say that S is the set of solutions to the inequality. It is described by all real numbers x, such that x is strictly greater than minus 2 over 3. And in interval notation, very similarly, we have minus 2/3 up to infinity. Importantly here, since minus 2/3 is not part of the solution set, we put a round bracket on that side, and we never put a square bracket on the side of the infinity. So I hope that is clear. If there are any questions at any point, please shout. Otherwise, I think we can move on to another example. So here we have the inequality, two inequalities written as 1, which we can solve. So 4 less or equal to 3x minus 2 and 3x minus 2 less than 13. What we do is we can take the 2 over on both sides. So here we will add 2. In the middle, we'll add 2. And on the right-hand side, we add 2. In the middle, minus 2 and positive 2 cancel. On the left-hand side, 2 plus 4 is 6. On the right-hand side, 13 plus 2 is 15. And so we have this inequality, 6 less or equal to 3x less than 15. And thereafter, we divide by 3 throughout. And since 3 is a positive number, the direction of the inequalities do not change. And so we get a final solution of 2 less or equal to x, which is less than 5. In set builder notation, the solution set looks as follows. And in interval notation, it's all numbers from 2 to 5, including 2, but excluding 5. And graphically, like we had before, this blue line represents the solution set. Obviously, since we included 2, we have a shaded circle at 2, an unshaded circle at 5, since 5 was not part of the solution set. And as I've shown, we have the set builder notation as well as the interval notation. Either one is acceptable. Notation does not really make much of a difference. Now here we get into some more interesting inequalities, in that we cannot just solve them by the traditional or elementary methods of taking stuff over to the other side and dividing by factors. We have, in particular, we have these polynomials of degree 2 or more, which are part of an inequality. So for example, here we have a degree 2 polynomial, or a quadratic polynomial, x squared minus 5x plus 6 less or equal to 0. Now, how do we solve this particular inequality? We cannot just do as with equations. So what I'm saying is, if you had the following equation, x squared minus 5x plus 6 equals 0, what you usually would do is you'd find factors of 6, you'd factorize this thing, and then from this step, what you do is you would say either x minus 2 equals 0 or x minus 3 equals 0, and you can conclude and solve this thing quite easily by saying that either x equals 2 or x equals 3. Now, this does not work with inequalities. However, the part where we factorize, that is important. In fact, we need it to solve the inequality. So here we start by factorizing. Whenever we have something like this, we want to factorize as much as possible and get as many of these factors as possible. And the reason for that is that depending on what x value you put in for x, this factor here could have a sign which is different to this one here. For example, for one number x, x minus 2 could be positive, and for that same number x, x minus 3 is negative, in which case this entire thing would be a positive times a negative, which is a negative. Or it could have been the other way around. Both of them could have been negative, or both of them could be positive. And you see how that these sign changes of each factor affects the sign of the entire expression. So you need to check this. And also the important thing is that the signs of each factor changes independently of the other factors. And that we will sort all of this information out in a table. We refer to this as the table method for solving the inequality. But for that, we need to factorize our given polynomial into as many factors as possible. So we have that in the equation, x squared minus 5x plus 6 equals 0. There are two solutions, x equals 2 or x equals 3. These numbers are called our critical numbers, or critical points. We get all our critical numbers and we split up the real number line into as many pieces. So here we have two critical numbers. We're going to split up the real numbers into firstly this interval here, minus infinity to 2, 2 to 3, and 3 to infinity. And that's important as that we'll fill that as information in our table. So let's look at how this is done. So, but also keep in mind, we are looking for all x values such that this quadratic expression is less or equal to 0. We want to check the sign of x minus 2 times x minus 3, depending for each of these intervals. And so we start by drawing our table. Remember, we broke up the real line into 3 different intervals here. Our first column here will be for those particular intervals, minus infinity to 2, 2 to 3, and 3 to infinity. Then each column thereafter will be building up our given expression. Remember, this final column here is our given expression, x squared minus 5x plus 6. And remember, we are solving the inequality where this expression is less than or equal to 0. So we begin by filling in this interval column, and then we check each factor. We check the sign of each factor according to that particular interval. For the first interval, minus infinity to 2, if you plug in any number from that interval in the factor x minus 2, you will see that the answer that comes out is negative. And hence, you put a negative sign there in that entry for the table. Then you check the same thing for the next factor, x minus 3. You put in any number from minus infinity to 2 into x minus 3, the answer will be a negative. Now to compute the sign of this x minus 2 times x minus 3, you're going to check the signs from the previous two columns and multiply them out. A negative times a negative is a positive, and so you have the sign of this last column for the first interval. So that one is done. Now you will do the same thing for the next two intervals. In the interval 2 to 3, all numbers are bigger than 2. So x minus 2 is going to be positive. So you put in the sign plus. However, in the interval 2 to 3, all the numbers there are still smaller than 3. So x minus 3 is negative. And thus, the sign of the last column will be positive times a negative to give you a negative. And finally, all numbers in 3 to infinity in this interval will make both of these factors positive, in which case the sign of the product of those two factors is positive. Now, how do we get the solution for this inequality from this table? Well, we go back to our inequality. We wanted this expression, which can be factored out as the product of these two factors. We want it to be negative. So which values of x will guarantee us a negative answer? We check the sign of the column or of the last column, and we see that it is negative precisely on the interval 2 to 3. So our solution set is all numbers x between 2 and 3. Furthermore, because we had an inclusive inequality, the numbers x equals 2 and x equals 3 also solve the inequality. So our final answer would be this interval 2 to 3 inclusive. Are there any questions? If not, I think there are a few more complicated examples or a few more examples of this nature involving more factors. So let's take a look at them. Here we have a cubic polynomial. We can take the 4x over, take out x as a common factor, thereafter factorize this quadratic bit to get x times x minus 1 times x plus 4. Now this splits up our real number line into 4 different pieces or 4 intervals. We have 3 critical numbers, x equals 0, x equals 1, or x equals -4. And we want to solve this inequality here when this expression is strictly positive. So these critical points, x equals 1, -4, or 0, obviously will not form part of our final answer. So we got the numbers -4, 0, and 1 on the number line. We split up our number line according to these critical points, -infinity to -4. Obviously, we arrange it in increasing order or numerical order, -4 to 0, 0 to 1, and 1 to infinity. So we will perform the same table method for all 4 of these intervals. Once again, this first column represents our intervals, which we obtain from the critical points. Then we build up our given expression, which is represented in this last column. Remember, we wanted it to be strictly positive. We need to allocate a column in the table for each given factor. And then we simply check the sign of these factors for each interval. And we do that by substituting in any value from that interval in the factor. So for this first factor x, in the interval -infinity to -4, it is always going to be negative. From -4 to 0, still negative, and thereafter it is positive. Then we move on to the next factor, x minus 1, plug in numbers from this interval -infinity to -4. It turns out that all those numbers or any number in that interval will render this factor negative, and this continues until the interval 1 to infinity. We do that for the factor x plus 4 as well. And to get our signs in the last column, we multiply we multiply the rows out horizontally. So for the first entry here, it will be a negative times a negative, which is a positive, times a negative is a negative. So that's correct. For the next interval, this cubic expression will take on the sign plus. And why is that? Because a negative times a negative is a positive, times a positive is also a positive. So that's correct. The next one is negative. Why is that? Positive times a negative is a negative, times a positive is a negative. So that one's correct. And the last one, we see that all the factors are always positive. So positive times positive times positive is positive. And then to solve the inequality, we read off this table where the expression is positive, because the initial question was for when this expression is positive. We see that it is positive on 2 pieces of the real line, or 2 intervals. So from -4 to 0, and or on 1 to infinity. So if you take any number in any either of these intervals, and you plug it into the original, you'll see that the inequality is satisfied. And remember, since it was a strict inequality, we do not include the numbers -4, 0, or 1. So there's round brackets there. So here it is in set builder notation, either x belongs or lies between -4 and 0, or it is strictly bigger than 1. And it can also be represented in interval notation. Any questions? All right, then let's move on. What happens when we have a quotient of two polynomials in an inequality? Well, we once again want to break up we want to have as many factors as possible in order to compare the signs of each factor. However, you'll see here, the solution is not too difficult. So what we do is we will take the one across. So you will have this quotient here, -1. Then you have, then you use a lowest LCD, or lowest common denominator. -1 can be written as x minus 4 over x minus 4. Simplify this expression to get 3 over x minus 4 strictly bigger than 0. To solve this inequality, we need to compare the signs of the numerator and denominator on this side here. So, but notice here that the numerator is a constant number, which is always positive. And therefore, the sign of this thing here, of this expression on the left, will depend solely on the sign of the denominator. In other words, because 3 is positive, this is positive precisely when x minus 4 is positive, since positive 3 has no influence on the sign of the entire expression, 3 over x minus 4. And then it is a simple matter of solving this inequality in that x is strictly bigger than 4. And so all numbers bigger than 4 will satisfy the original inequality. Are there any questions with this particular example? Let's move on. It seems like it's getting steadily more complicated. Here we have in our numerator a quadratic expression as well as one in our denominator. We see that our denominator is nicely factorized. However, the numerator is not. We can rectify this by factorizing x squared minus x minus 6 into the product of x minus 3 and x plus 2. Once again, we have 3 critical numbers. In the numerator, we have from the numerator we have 2 critical numbers, 3 and -2. From the denominator, because we can't have division by 0, if the denominator is 0, that number is called a critical number as well. So x plus 1 being 0, or in other words, x equals -1, will be a critical number. Once again, we'll split our real number line into a few pieces according to the critical numbers which we found, and it is as follows: -infinity to -2, -2 to -1, -1 to 3, and 3 to infinity. Notice once again, we are looking for when this entire expression is strictly negative. We'll perform the whole table method once again to solve this inequality. So the first column will be for all our intervals, and we build up to our expression given in the last column. Remember, what we wanted was when this expression is strictly negative. X minus 3 will be positive only for numbers x bigger than 3, otherwise it is negative. So the signs here are all correct. For numbers, you can test this out for taking random numbers in each of these intervals. You'll see that if you plug in x minus 3, the answer is negative. However, for numbers coming from this interval, if you put it in x minus 3, it will be positive. Likewise, you can test that out to get the sign of x plus 2 in each interval here. And if you blindly test out the sign of x plus 1 all squared, you'll get that all of them are positive. However, if you make a clever observation in that the square of any number is always positive, you can fill in the information for x plus 1 squared in that for each interval it is always positive. Furthermore, if you notice that we in fact did not need to include a column for x plus 1 squared for the simple reason that it's always positive. So it will not affect the sign of the expression. In any case, we check the sign of our last column by multiplying throughout. A negative times a negative is a positive, multiplied by a positive is a positive. A negative times a positive is a negative, times a positive is a negative. Negative times positive is negative, times a positive is negative, and pluses throughout multiplied will give you a positive number. And since we are looking for when this expression is strictly negative, we select these two rows here. And thus our solution is -2 to -1 or -1 to 3. Once again, are there any questions with this example? Okay, let's move on to absolute values, and inequalities will play a big role in defining the absolute value as well as some rules associated to it. Now, the absolute value of a number A is denoted by these two bars on the left and right of that number, and it is simply the distance of the number to the number 0 on the number line. So since we are measuring distance, we have that the absolute value is always a non-negative number. So the absolute value of a number is greater or equal to 0 for all numbers A. For example, the absolute value of 3 is equal to 3. In other words, if you look at the number line, that is 0, that is 3, let's say is -3, then how many units you need to move to go from 3 to 0 or 0 to 3? Well, that's precisely 3 units. Now, the absolute value of -3 is also 3. And remember, absolute value is the distance of that number from the number 0. How many units do you need to cover to go from the number -3 to the number 0? Well, once again, it's 3 units. So that is why the absolute value of -3 is also 3. The absolute value of 0 is 0. There's a 0 distance from 0 to itself. Here we have √2 minus 1. Its absolute value is just itself. Why is that? Well, √2 is strictly bigger than 1. And so √2 minus 1 is positive. And like we saw with 3, if the number inside the absolute value is positive, then taking the absolute value does not change its sign. However, pi is bigger than 3, so 3 minus pi is negative. If you take its absolute value, it must be the other way around. As we had seen with -3, we took the absolute value of -3, and that gave us the answer +3. We always want a positive answer. So the absolute value of 3 minus pi must be pi minus 3, which we know is positive. Don't worry about what I just said in the last 2 cases here. If it seems a bit confusing, there is a strict rule or method in which the absolute value is defined, and it's on the next slide. And this is how it is. The absolute value of a number is of a number A is A if A is equal to 0 or positive. Otherwise, it is minus times that original number if A was given to be negative. There is another way to define the absolute value, and that's in terms of the square root symbol. Now, when you solve equations before, for example, if you had the equation x squared equals 4, what you do is you take the square root on both sides, but you'd indicate a plus or a negative on the side of the solution. The absolute value is defined as the following. So if you're given the absolute value of A, what you do is you're going to square it and then take the positive square root thereof. So for example, if you are, let's go back to -3. Remember we said that this answer is 3. If we go by this definition here, then we need to say that this is minus times -3, which is 3. Alternatively, with the square root definition, what did I say? We take the number inside, -3, we square it, and then we take this, the positive square root of it. -3 squared is 9. The positive square root of 9 is positive 3. So you see these answers coincide. So you can remember either definition, it makes not much of a difference. And like I said, this is an alternative definition for the absolute value. Now, for example, if we are given a variable inside the absolute value, let's say the absolute value of 3x minus 2. If we want to drop the absolute value sign, what must we do? We'll recall how we defined this. We defined the first definition of it was a piecewise definition. The absolute value of x is positive x if x is not negative. Otherwise, it's minus times the given x if x is negative. We can apply this principle here. So if we want to drop the absolute value, we need to bring in the piecewise symbol. The piecewise manner in which we write this out. So 3x minus 2, its absolute value is equal to 3x minus 2, provided that 3x minus 2 is greater or equal to 0. Otherwise, it's equal to minus times 3x minus 2 whenever 3x minus 2 is less than 0. Now notice that we can solve this set of inequalities in terms of x only. And so we can write this out a bit better, in that the absolute value of 3x minus 2 is equal to this if x is greater or equal to 2/3. Otherwise, it is 2 minus 3x if x is less than 2/3. Are there any questions with this definition of the absolute value? Okay. Now the graph of the absolute value function is important. It's also easy to remember. It will help you remember some more rules, which we'll look at in a few moments. If you recall the original y equals x, so ignore this for now. How did it look? It was just a straight line, 45 degrees inclined from either the positive or either the vertical or horizontal axis. Now, for all x smaller than 0, you see you have this piece over here, which lies below the x-axis. Now, when you take the absolute value, what happens is that that piece flips up or is reflected along the horizontal axis. And so you obtain from this simple observation, the graph of the absolute value function. Remember, this is always greater or equal to 0. So you can't ever have that it is below the horizontal axis. So some properties of absolute values. Let's say a and b are any real numbers and n is any integer. Then the absolute value behaves nicely in that if you multiply two numbers and then take the absolute value, that is equal to first taking each of those numbers' absolute values and then multiplying out the result. Likewise, if b is non-zero, you can sort of distribute the absolute value over the numerator and denominator. And thirdly, if you have a to the power n, so if you're taking powers of a, and if you then take its absolute value, in other words, what happens is you can take out n from the absolute value. You can first take the absolute value of a and then raise it to the power n. I think these rules are not too difficult to understand. They are obvious and they should be obvious. If they were not true, then we would have cause to worry. But next set of properties are a bit more interesting and useful for solving equations involving absolute values. So this number 4, if we are given that the absolute value of some variable x is equal to a, then we will always have that x is either positive or negative a. Number 5, if we have the inequality, the absolute value of x is less than a, then this is true precisely when x lies between minus a and positive a. And finally, if the absolute value of x is bigger than a, this is true precisely when either x is bigger than a or x is smaller than minus a. Now you can obtain all three of these rules, 4 to 6, by looking at the sketch of the absolute value. So let's go back to the sketch. The first one says that if the absolute value of x equals some number, let's say in this case we're looking at 2, then this is true precisely when x is equal to plus or minus 2. So the solution to this particular equation is the numbers positive 2 and negative 2. How do we solve equations by looking at this graph? Well, here we have that y equals absolute value of x. We want all values of x such that y equals 2. Let's go to y equals 2. It's represented by this line here. Let's find all x values which intersect this red dotted line and the absolute value sketch. Well, there are only two x values. That's precisely when x is negative 2 or x is positive 2. Like I said, you can obtain these rules from by looking at the sketch of the absolute value function. The next rule said that if we have that the absolute value of x is less than a number, this happens precisely when x lies between c and minus c. So instead of c, let's say we have 2. So this is what the rule said. Let's see if it's true. Let's go back to our dotted line. We wanted all values of x such that y is less than 2. So we will ignore everything above the line, above the dotted line y equals 2, and then we read off the resulting x values. So everything below this line, or everything that I haven't shaded, that is true whenever x lies between minus 2 and 2. So once again, you can use the sketch to obtain these rules. The last rule said that if the absolute value is bigger than some number, that is true precisely when one of two things happen. Either x is bigger than 2 or x is smaller than minus 2. Once again, we look at our dotted line, y equals 2. We want all those numbers x such that this graph lies above this dotted line. So we will shade in below here, and whatever piece of the graph above this in the unshaded area will read of that solution. Remember, this corresponds to x equals minus 2. This corresponds to x equals positive 2. You see that this graph is only above the shaded area when x is less than minus 2 or x is greater than 2. Once again, you can look at the sketch and obtain the property, or all three of those properties. And they are very useful in solving these inequalities and equations involving absolute values. Are there any questions? So once again, here's the properties I've been talking about. And now I think we can do some examples. So let's say we want to solve this equation. The absolute value of 3x plus 5 equals 1. We are expecting to get two solutions. Firstly, we need to drop the absolute value sign. So either everything inside the absolute value is equal to positive 1, or everything there is equal to negative 1. Then it's a simple matter of solving these two equations in the usual manner. For the first one, we get that either x is minus 4/3. So what we did was we took the 5 over and divided by 3. In the second one, we did the same thing by taking the 5 over. However, there we had a minus 6. And then solving for x, we get two solutions. X is minus 4/3 or x equals minus 2. If you plug in this, any of these two solutions in the original equation, you should have no contradictions on the left-hand side. The left-hand side and right-hand side should agree. Remember, the absolute value simply takes away the negative sign. So if you have this, for instance, that's equal to positive 5. Here we have an inequality. Absolute value of x minus 4 is less than 1. Remember the property, if something inside the absolute value is less than a number c, this is true. Or you can go, the next step from here is to drop the absolute value, but then you need to have two inequalities, x less than c. At the same time, it must be bigger than negative c. So here it will be, if we want to drop the absolute value, we take everything inside there. That must be less than 1, but at the same time, it must be less than, it must be bigger than minus 1. Now you add 4 on each of these, and you have the solution. X lies between 3 and 5. Any questions? We can do the same thing. Let's say 2x plus 3, its absolute value greater or equal to 5. To drop the absolute value, we need to use properties 4 and 6. This is equivalent to, so remember, if this is true, then if you want to drop the absolute value, you must say everything inside the absolute value is bigger than c, or it is smaller than minus c. So here, the stuff inside the absolute value is 2x plus 3. To drop the absolute value, it needs to be greater or equal to 5, or it needs to be less or equal to negative 5. Don't worry about whether it's a strict inequality or non-strict inequality, those rules 1 to 6 always apply when you are using absolute values. So now you can solve both of these inequalities in the usual manner. The first inequality gives you a solution of x less or equal to -4, while the second one gives you x greater or equal to 1. And so your solution set is the union of these two intervals. All numbers between -infinity and -4, including -4, and all numbers between 1 and infinity, including 1. There's another property associated with the absolute value, and that is called the triangle inequality. So if you take two numbers, a and b, and you add them and take the absolute value, that is always less or equal to the absolute value of the first number plus the absolute value of the second number. And why is it called the triangle inequality? Well, it follows this basic principle here, in that if you have a triangle with 3 points, A, B, and C, if you want to get from A to B, then the shortest distance between A and B is the straight line or the side of the triangle which joins A and B directly. And that will always be smaller than if you had to travel from A to C and then going from C to B. So this absolute value of A plus B is less or equal to the absolute value of A plus the absolute value of B. And how is this useful? Well, for example, let's say we are given that for some numbers x and y, the absolute value of x minus 4 is less than 0.1, and the absolute value of y minus 7 is less than 0.2. We can use the triangle inequality to estimate the following: x plus y minus 11, or the absolute value of x plus y minus 11. Now, how do we do that? Well, we'll use our two given facts. So let's say A equals x minus 4 and B equals y minus 7. We'll use the triangle inequality for that. We can break up minus 11 into minus 4 and minus 7. Minus 4 minus 7 is minus 11. And here we have that this here is equal to A. This here is equal to B. This thing must then be less than or equal to absolute value of A plus absolute value of B. In other words, this thing must be less or equal to the following expression. And we were given the information that this term here is smaller than 0.1. And at the same time, this term here is smaller than 0.2. So we can estimate that our given absolute value expression is less than 0.3. Are there any questions? So the slides I used were adapted from Appendix A of James Stewart's calculus book for calculus of one variable functions. Appendix A, as I said. There are many exercises in the textbook, and the format of this lecture followed exactly the format which is in the textbook. So if there's anything that is not clear, you can refer to the textbook. I'm assuming that this textbook is very widely used in South Africa for first-year calculus students. But this example concludes the lecture for today. There will be a lecture at the same time tomorrow. I think it's to do with an introduction to matrices and linear algebra. But other than that, thanks for attending. I think these slides will be made available to the participants. Yeah. Thanks for attending. Enjoy the rest of your evening.